Okay, guys, so I wanted to make a little video here for you about a paired t-test. It says when paired data result from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the differences in the pair. So if the conditions for inference are met, we can use one sample t procedures because we're still talking about means, and we can do inference about the mean difference, mu sub d. So this is new notation, mu sub d, okay, for mean of differences. And then we call, usually when you have a matched pairs design in your study, so a matched pairs design in your study, that leads to, we do matched pairs design that leads to paired t procedures, okay. So I'll show you how to do that. I'll read this with you very quickly, and then we can get into the actual test. So it says researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So at the end of each 2-day period, they were given a test and they gave a score, a depression score. Okay? So 2 days without caffeine, 2 days with, or 2 days with placebo, 2 days with capsules with their normal caffeine intake. Okay? And then here's the data, the results. So if I want to talk about the mean of differences, or the mean difference, then that means I have to subtract things. All right, so I don't want to, this, if I average all of this data up and get a mean, all right, that would, sorry, not mu, get a mean, that would be one mean, and then if I average all these, that'll be a second mean. What do I do with that? How does that work? We haven't really spoken about anything like that. So we are going to do two sample t-tests next chapter, but not yet. And this is not two samples. This is really the same group of people who got two treatments in randomized order. So it's not really two samples. It's not really two groups. It's the same group in a matched pairs design. So the way we do this is to subtract the scores and get the mean of the differences. Okay, so we subtract the scores, and if it were me, I would subtract placebo minus caffeine. I would do placebo minus caffeine, because if you look at the scores, placebo look like they're bigger numbers, and so I'm going to get positive numbers when I subtract. That's usually something we like more in math. Okay, so I would do placebo minus caffeine. Now, how do I do this? That's part of the test. You enter it in your calculator, and then you do some fancy footwork there. So I'll show you how that works. But so that's the idea. I want to find the mean of the differences, so I would do 16 minus 5 and 23 minus 5. But we don't want to do all this by hand. Okay? And so for now, I think the best thing to do is just to enter that in your calculator, go to Stat, Edit, and then I just did list 1 is the caffeine scores, list 2 is placebo scores, just because that's the order they gave them to us. But then you can go to list 3 and hit enter up here, and then you can do what we've done before. I believe we've done this before. You do list 2 minus list 1, and you get all the differences, right? So here's all the differences, and we want to do a test about the mean of the differences. All right, so that was pretty easy. Did all the math for us. And so we'll proceed with that in a second, but there's a question: why did the researchers randomly assign the order in which subjects received placebo and caffeine? And you can just say, since the order of the treatments may be a confounding variable. Okay, so if everybody got caffeine first and then placebo second, it's likely that their depression scores would all be, affected in some way by that. And maybe there's some lingering caffeine in their system or whatever. So if we randomize the treatments, then order of the treatments is not a problem because we've controlled for that confounding variable, okay, by randomizing the order. And then the treatment is switched. So still the same person gets both treatments in any case, but the order in which they get the treatments is randomized. Okay, so that's the reason for that. And then it says carried out the test. So let's do the actual test. All right, so we still do the same thing. State, and what are we trying to do? We want to perform a test of and write our hypotheses. And our hypotheses would be null hypothesis. Well, if we're saying we want to do a test about the mean of the differences, null hypothesis is that there is no difference. So if there is no difference, then the mean of the differences would be 0. Okay, that's always the null hypothesis, a statement of no difference. So mu sub d is 0. There is no difference in depression scores with or without the placebo, or with or without caffeine. Okay, and then my alternative hypothesis would be, and what did they say? They want to know whether being deprived of caffeine would lead to an increase in depression. All right, so placebo first means I'm deprived of caffeine, and would that be a number that is bigger than having caffeine? My depression score would be bigger with a placebo, in other words, no caffeine, than with caffeine. So what we want to do is, in our subtraction here, we want to say, is the mean of the differences greater than 0? In other words, without caffeine, was I more depressed? All right? And then we say, where we have to define our parameter, where mu sub d is the mean of the differences in depression scores. And you have to say which way you subtracted. We subtracted placebo minus caffeine. Okay, so lastly, you have to state your significance level, let alpha be 0.05. They didn't give us any of that, so we're just doing it. All right, the plan step. Okay, so we say if conditions are met, we will perform a paired t-test for mu sub d. Okay, and condition. So please, this is a name that you have to know. Name the procedure, and then we do random. But random here is different because there was no sampling, but there was randomly assigning of the treatments. Okay, random assignment of the treatments. So we just say that the treatments were randomly assigned to subjects or individuals. Okay, and then independence, also different. There's no 10% condition, because 10% condition means I'm sampling less than 10% of the population. So that's not what's happening here. What's happening here is we want to say it is safe to assume that people's differences in depression scores are independent. Okay. So if my depression score turns out a certain way, that doesn't impact yours, of course. So our depression score differences are independent of each other. And then normal. So normal, how do I do that? The sample size is less than 30, n equals 11, right? Didn't they say 11? 11 volunteers. So you have to make a box plot again, okay? So you have to go here, and remember we have the differences right here, and you have to make a box plot, so second stat plot, and go here, turn it on, and we'll do, again, the box plot that shows outliers, and we'll go down, and actually our differences are in list 3. Enter, and we can do zoom stat, which is 9, and there's my box plot. We can trace. So minimum is -1, so we go back here. We need a scale here, so we'll go -1, and then next one, my Q1 is 1, my median is 6, okay? So Q1 is 1, and my median is 6. All right. Before I do that, what's the next one? My Q3 is 13, okay? So right there, all right? And so my median's right there, and then we'll do, my max is 19, all right? My max is 19, let's see. Okay, so there's my max. So you can see that the graph is slightly right skewed, okay? Not much, but slightly right skewed. So we'll say the box plot is slightly right skewed. And our sample size is only 11. So according to our rule, this is actually a situation in which we shouldn't really want to proceed. We want symmetry with a sample size less than 15. So we will say proceed with caution or something like that. Okay, proceed with caution, because that is not the ideal situation. All right, and then we say do. And so we use the same old t-statistic we used before. So t equals x bar. In this case, it would be basically mu sub d minus, no, we can't do that. It would be the mean of the differences minus mu sub d over s sub x over n. Okay? And is this root n? I think it's root n. And then we would do the calculation. So we would get x bar, plug it in. Now, where do we get this stuff from? We go to, actually, I think we can just do the tests. So we do stat tests, and we do a t-test. So you don't, since we're just looking at one set of numbers, okay, the differences, we'll just do a regular t-test. Okay, we'll just do a regular t-test on our calculator. So we do t-test, and we go to data, and the data, the mean that we're looking for is 0. The null hypothesis mean was 0, okay, equals 0. And then our data is in list 3, and our alternative hypothesis was, if we look here, greater than. Okay, so our alternative hypothesis was greater than, and then we go down to calculate, and we get everything we wanted. Okay, so I have my t-statistic is, let's see, 3.530. So there's 3.53. And then we can do the p-value. So the p-value is the probability that t is, and look at the alternative hypothesis, greater or equals to 3.53. And that gives us a number, and the p-value is 0.00272. Okay, 0.00272. Remember, if it's a T procedure, you must list degrees of freedom. So the degrees of freedom here is 10, which is 11 minus 1. Okay, so that's our do step, and now we have our conclude. And for the conclude step, we say, since the p-value, which is 0.00272, is less than alpha, which is 0.05, we reject the null hypothesis. Okay, so the null hypothesis, we reject it. The mean difference is 0. We have sufficient evidence to conclude that the mean of the differences in depression scores is greater than 0. Which, let's see if we answered the question. Question was, would being deprived lead to of caffeine lead to an increase in depression? Okay, so we can say caffeine deprivation led to an increase in depression score. Something like that. Okay? And then it says construct a 90% confidence interval for the mean difference in depression scores. And you just do the same thing we've done before. Our, what was this? X bar plus minus T star times S sub X over root N. And you just go create your confidence interval the same way we used to. Okay? So I don't really want to go over that. I think that's okay. This was our whole chapter 8. And then you can read over the rest of this. It's an interesting little hypothesis test this because it's an experiment. Okay, so this is really our first experiment we've done, and we actually have causation. Caffeine deprivation led to an increase in depression scores. We actually have causation here because this is an experiment. Very interesting. Okay, hope that helps you guys.